This is a lesson on section 1.6, and we are talking about relations and functions. So we're going to first start out with a couple just general ideas. We're going to think about people and their phone numbers. So can a person have more than one phone number? Absolutely. I can have a cell phone, I can have a home phone, and maybe I have a work phone. So that is one person with more than one phone number. Can a phone number belong to more than one person? Yes. If you have a home phone, that might belong to everyone in your house. So again, these are both ideas where we have one item that has more than one outcome that it belongs with. So if we talk about a height, can a person have more than one height at the same time? So if I measure myself accurately and I'm 5'7", and I get measured right after that accurately, I'm still going to be 5'7". So one person should have one height. Can the same height belong to more than one person? Yes, I can be in the room with several other people who are also 5'7". So here is an idea where one person will only have one outcome for height, and a height can have multiple outcomes matching with the different people. So this all brings us to the idea of talking about a relation. A relation is a pairing of input and output values. So when we talk about this, it can be shown as a set of ordered pair XY, where X is the input and Y is the output. So we have some examples here. We want to talk about the domain and the range for this relation. And so I want to remind you that this relation is in roster notation. I can only use roster notation if I have a discrete relation, and in this case, this one is finite. So I have 1, 2, 3, 4, 5 ordered pairs. So it's discrete because it's not continuous between 2 points, and it's finite because there are only 5 ordered pairs. Domain is the X values. So if we come through here, the X values sit right in front, X comma Y, and it's proper to put it in roster notation for this and to list them in order from least to greatest. So we would just write in 100, 120, 140, 160, and 180. And so those are all of the X values for this relation. Next thing we're going to talk about is the range, and the range simply the Y values. Now when you look at your Y values, I have a 5, another 5, a 6, and a 12. So when you're talking about the range or the domain, you don't repeat any numbers. So the Y value could be a 5, it could be a 6, or it could be a 12. So this is the possible Y values. You can see that I have now lost. I don't know what the 100 goes with. I don't know what the 140 goes with. I just know these are my possible X values and these are my possible Y values. All right, and the next one we have something called a mapping. So if you see the term mapping, this is what it looks like. And in this case, we're mapping types of trees instead of numbers. So if we look at this, this is our input, or our X value, the genus, and this is the Y value, or the output. So the genus of a tree can have more than one species. So if we were talking about ordered pairs, just to give you the idea, the ordered pairs would be oak, comma, red. Another ordered pair would be oak, white. And we'd have maple that maps to red. And we have maple that maps to sugar. So we have 4 ordered pairs here. So we can transfer these ordered pairs from our mapping. But we want to talk about the domain and the range. So the domain here are the oak and the maple genus options. And that's it. And the range are your species. Red, white, and sugar. And that's it. That is your domain and range of something in roster notation and a mapping. We'll also be talking about domain and range from graphs. So we're going to come back to these 2 examples and talk about if these are functions or not, but we're going to start and define functions. And I just realized that I skipped right here. So let's come back up here. In a relation, we talked about X being the input. That is the term domain. All right, the domain gives us the set of input values, y is the output. We refer to that as the range. The range is the set of output values. So we found the domain and the range. All right, so on the back, we are now going to focus our attention on the idea of something being a function. So a relation is the general idea. Every x has a y. So a relation in which the first coordinate is never repeated is called a function. In a function, there is only one output for each input. So every element of the domain is mapped to exactly one element of the range. We're saying the same thing in three ways. Only one output for every input. Element in the domain is mapped to exactly one element in the range. But in other words, every x, there's exactly one y. That's it. I like to sort of say every x has exactly one y. Every x has exactly one y. That is the phrase you'll hear me saying. Every x has exactly one y, and we abbreviate the word function as FCN. That way we don't have to write it out each time. Okay, so we want to look and see if every x has exactly one y. So we start off with some general ideas here. So we want to tell if it's a function and why or why not. So we're talking about the store, items in a store to the prices on a certain date. So the items in a store should have the same price on a date. So if I go in to buy a 20-ounce soda, that same 20-ounce soda should be the same cost. So one item should have one price. We're not worried about sales or the next day when something goes on sale. We're talking about the same thing. So this would be considered a function because every item should have one price. So every item is exactly one price. So that makes that a function. Now to contrast that, we're talking about types of fruits. So types of fruits to their colors. So a good example would be an apple. So if I asked you to run to the store and get me an apple, you could be picking a yellow apple, a red apple, maybe a green apple. So this is an example where one input, I wanted an apple, that's what we're going for, could have three different outputs. So this would not be a function. And why is it not a function? Because some fruits have more than one color. Have more than one color. Now I'm being very careful about the wording. It's not that all fruits have more than one color. It's not that every fruit. It's only some fruits like apples and apples and grapes. They have different colors. All right, now we have these two more examples. They're both in roster notation. So the quick check is the x repeated? Okay, that's the quick check, but we have to dig a little deeper. So I've got -2, -1, 0, 1, and 2. Does the x repeat itself at all? So since it doesn't repeat itself, there's no chance that I'll get a second answer out for that same value. So this is a function. Now telling me that x does not repeat is not a good enough definition. So the x does not repeat, which means every x has exactly one y. So that is our reasoning. Every x has exactly one y. All right. Now, looking at our next example, we look and we see -5, 0, 5, 6, up, here it is. Do we see this? X repeats itself. So when x is 2, I have two different outcomes. So it's not just that x repeats itself, it's the fact that when x is 2, I could get an outcome of 0 or an outcome of -5. That makes it not a function. So when I say, what's x, what's y when x is 2, some of you might tell me it's 0, some of you might tell me it's -5. You're both right, but that makes it not a function. It's not a function, and you could say that some x's have more than one y, you could say one x has more than one y, but you cannot say every x. That is the only x that has more than one y. So when x equals 2 more than 1y. Now, just to give you a quick idea, if this ordered pair was different, if this ordered pair was, I had 2, 0, and then I had another 2, 0, that's okay. Because even though the x repeats, I still only have one outcome. So if this was 2, 0, it's still a function. Now, the other thing that bothers some people over here is they want to say this is not a function because the y repeats. See how this has a -2 and that has a -2? The x, as long as it only has one outcome, can share a y with another x value. All right, if you can take a minute, let's flip it back over to the front. I want to know if this example A is a function. So we looked at the x and it did not repeat. So even though the y repeated, this x only has one outcome. There's no other x that's 100 that has another outcome. So this one would be considered a function because every x has exactly one y. Our mapping, we can actually see it's not a function because this one maps to 2 different outcomes. So that makes it not a function. And you can also see that oak went with red and oak went with white, and same thing with maple. All right, so if I'm looking at ordered pairs or a mapping, every x can only have one y. But there is a nice trick to talking about a graph. It's called the vertical line test. Vertical line test, and we can abbreviate that as the VLT as long as you remember what those terms stand for. So the rule is if any vertical line passes through more than one point on the graph of a relation, then the relation is not a function. So if any vertical line passes through more than one point on the graph of a relation, then it's not a function. So if I draw a vertical line, I'm going to draw mine right here, and it hits more than one point, which it does, then it's not a function. So let's do that. Not a function. So use a vertical line test. Is it a function? If not, identify 2 points. Well, first of all, why is it not a function? We can simply say that it fails the vertical line test. But why can we use a vertical line test? Because we're testing the x values. This equation for this vertical line is x equals 2. If you remember that, a vertical line does not fit the rules of y equals, and in a vertical line the slope is undefined because you rise 1, you run 0. So with that in mind, this fails the vertical line test. So this point is 2, and we're going to estimate it to be 1.9. And this point is also x at 2, and I'm going to estimate it to be -0.25. We're just estimating there. So that x value has more than one y. So the vertical line test is connected to x only having one outcome. All right, let's look at this next one. We'll go ahead and put some arrows on here. And so this would keep going up and this would keep going down. So is it a function? No matter what vertical line I draw, it's only going to hit one point. So it is a function because it passes the vertical line test. So our last one. These are both continuous graphs because the graph is continuous through points. This is considered a discrete graph because we have only these points and they're not connected, so it's not continuous. This also fails the vertical line test. Actually, it fails it in 2 places. Okay? So this is not a function because it fails the vertical line test. So to connect that again, let's use these 2 ordered pairs, and that one is at 1, -1, and this one is at 1, -4. And so you can see when x is 1, we have 2 y's, and same idea over here. When x is -2, we get out a 3 or a 1. Now, we're going to do a little bit more with domain and range of graphs. We are also going to talk about the vertical line test later in the year when we do inverses, where we flip the graph and we flip the test to use a horizontal line test.